Good afternoon. Can you hear me?
Yes.
Great, thank you. If you don't, please let me know. I have a question for you. Please lift your hand if you know what is the stage of flow. Flow. F-L-O-W. None of you? Unfortunately, only you? Congratulations. Last time when I had this previous presentation, I mentioned to you to look it up. Please do it. And I wish you to be in a flow stage most of your time. Not easy to get there. It needs a lot of effort to do that, a lot of skills. Then, if you achieve that, you will be happy. If not, maybe not. So, please check it up. Today, I'm going to talk about something what is very important and very interesting, especially for me, because I dedicated part of my life to study this. And then, since I have opportunity to talk to you today, I'd like to share my knowledge about it, what I studied for decades. As you know, the artificial intelligence is a very popular topic today, very popular. You could give an answer for your friend if he would ask you why it is so popular. You can answer probably very well why it is so important. One of the reasons that it can change our life. It can enhance our ability to do something because we are proud to be able to solve problems. And this new technology, the internet-based, computer-based new technology can help us to enhance our abilities significantly, not just minor changes, make some minor changes. It can change our life totally because we can do things much better than before. We can solve problems much better than before. You can ask what kind of problems? Huge range of problems. Almost any kind of problems, but involve some problem-solving skills. And we are very close to have this technology ready to use for broad areas. Fascinating. And you can learn it if you like. If you don't, you can be just like as today. But if you will put effort in it, you can learn a lot. And fortunately, these days, we have a great opportunity to do it efficiently. Way back, even 5 years ago, I'm not mentioning when I was in your age, sitting in these benches. Even 5 years ago, sorry for this, I need to switch it off. And I had to put it in airplane mode. Sorry for didn't do that before. So now we have opportunity to learn from the best ones. If you are fortunate, if you are wealthy enough, you can afford it. You can find it and you can do it efficiently. Way back it was not an option. You could dream to go to the best university on earth and to study from the best ones, but it was usually not feasible because you was not able to afford it, or your parents were not able to afford it, or maybe there was some regulation not to go there. These days, you can turn on your device, what is in your pocket, and you go there right away. And you need to usually pay a little money for that, not too much, a little amount, but you can do it right away. So, for example, today, I'm going to talk about artificial neural networks. This is the topic for today. It is the mainstream today. It wasn't mainstream even 5 years ago. Definitely not. 10 years ago, 20 years ago was definitely not. It was something like this, as I mentioned this picture before. When I started to teach this topic here, I believed it is very important to study the brain and very important to learn how does it work. Because one day, I didn't know that one will be there one day it can be a useful device for us to mimic the biological information processing device, and we can build something useful. These days, as you know, the whole picture flipped. The major area in the whole AI field is the deep learning using artificial neural networks. And today my goal is here to give you a summary. Since it is a very broad area and very deep area, not just the learning is deep, the area is very deep. We cannot go very, very deep everywhere. Rather, going in one specific area very deep, I like to give you an overview, to be able to see the whole picture, or at least you have an impression what is the whole picture. And then, if you are eager to do it, you can do it by yourself. You don't need to sit in these benches. You can go home, pay $10, $15, and you can learn it from the best ones. To help you to do that, for example, let me stop this presentation for a second. I go to the recommended literature here, and let me mention to you, I uploaded the previous presentation and the recent presentation, what I'm doing here now, to the Moodle. If you're interested, you can go up and you can look up something if you're interested. Let me mention here, I usually put a number on the slides. Just go back to a second for the presentation here. Here. You can see these numbers here. And if you want to make some notes, please write down this number here, and then you can go back to that presentation. You don't need to make a detailed notes if you don't like. But if you have some idea connected to that specific picture, make some notes. And when you start to study at home, pull this out and see. And remember what was your thought connected to this picture. So, for example, when I like to talk about this broad area, I like to mention the state of the art for you. Here it is. If you know Hungarian, you are fortunate, you can go to the Kürt Academy, one of the leading IT company in Hungary, who offer deep learning course for you. It will start next week, or maybe this week. I cannot recall exactly what day, but within days. If you like, you can go there. There is some entry test. You can do it. You can check yourself, your skills is enough for that or not. And then if it is enough, you can decide you will attend or not. But if you want to see the best ones on earth, you can go to, for example, Udemy or Coursera. As you know, unbelievable offering of good courses are available on the internet. Great ones, the best ones. What is monitored, what is quality controlled, what is tested. You can go up and see how many people already watched it. If you can see 100,000, it cannot be too bad. Because you can click right away. If it is too bad, okay, I need my time for something else, and click there and that's it. So if you are interested, for example, you can go on those courses and you can do it. Even 10 years ago, when the whole movement started, I learned there is a course, AI course available for foreigners or for other people who are not part of the university. And I looked in it and I thought, it's great. It is very close what I'm talking about here. Of course, I'm not on the top of the world because I'm not working for Google. I don't have that resources, what they have. And if somebody is interested, instead of listening to my talk here, can go there and check it up. And I announced it in a course. There was a big crowd here, maybe 200 people sitting in the course that time, this artificial intelligence course in Hungarian. And I mentioned to you, of course it is in English, so you don't have to have this obstacle to not to be able to go there. You need to be able to talk in English and read and efficiently. But if you do so, what is sometimes the entry requirement for getting to the school, you can take this course. If the end of the course you will bring the certificate for me, you don't need to take my course here. I will give you the grade. And I pushed it through the whole system here in the university system, and they let me to do that. So instead of giving exam for the students, here they showed me this Udemy proof that they finished the course successfully. I had to figure out what grade I will give, because it is not easy to tell what is 2 and 3 and 4 and something like that, because the grading is different there. But I did that. So finally, what do you think, what percentage of the course, what the students took this course in that time? What do you think? What percentage?
90 or not? 100?
No, 60, a little more than 60% of the, if I recall. So the larger part of the course took it. Not because it was so easy. They had to do it on a weekly basis. But finally they did it. And I hope it was not a cheating. And I hope they didn't do it because it was easier to cheat than taking my exam. And I hardly believe it was the case. And then, so it is great. So, here are these courses. If you like, you can go there and take it. The question, I will accept it or not, we can discuss it. If you are taking this course and it will finish before my course ends, we can discuss it. But my goal is here to tell you something, not just send you somewhere. Okay, go there and learn something there. It is not my goal. My goal is to tell you something here, what I understand from this area. So go back to this presentation. One of the first things what I learned, that the biological information processing processors, the devices, are not universal, like these days the computers. These days, our digital electronic computers are universal device. We can program for to solve any problems. If you know the algorithm, how to program it, we can write the code for it, and then it will solve it more or less efficiently. The paradigm, how we think, it is changed recently. The roots are going back for decades, but the big change happened maybe 10 years ago, when they learned we can use this artificial paradigm efficiently. We can do it for real good practical purposes. Now it has changed everything, and we can learn. As you listened last time, this Alexa, the behavior of the Alexa was partially based on this neural network things and so on. So, as I show you on this photo, this is the representation of the human brain. You have seen some numbers on it. It is called Brodmann numbers, because the guy who studied the brain made slices of it and painted them and noticed the structures are different. The interconnections are, the neurons are inside different. The scheme, the topology is different. That time they didn't know what the reason for this, but now we know. Because our brain is not a special, it is not a universal device, it is specialized for very specific tasks. For example, to visual processing or auditory processing or tactile processing to sense our senses and so on. So those are different processors, specialized for that specific task. Now these days, when we are using artificial neural networks, we like to somehow mimic this. We cannot make a universal artificial neural network, we need to make a specific one for some specific reason. Before I continue my presentation, I'd like to show you something what was fascinating for me some days ago. It is most recent information which I learned within a week or so. I'm sure you know what Tesla is, not the guy who invented many things. The guy who is producing fascinating technological achievements, for example, cars or SpaceX or so on. And I listened to one of these presentations of him, and I decided I will show you at least the beginning of it. The reason, not because I don't want to tell you many things during this class, I have many things to tell you, but I like to give you a motivation to do research in it and invest your time. Because my main goal would be in this course to raise your attention, to give some motivation to study. Because if I make you bored in this class, I did a terrible job. Because you will pass, likely, you will have a good grade here or some grade here. But if you don't like the topic, you won't study by yourself. But if you are interested, you will spend unlimited time on it. And only this unlimited time, what you can invest in it, can help you to go there, what can be fascinating for you and very useful. Let me show you this very short video, what I mentioned. Going back to this here, the very first one here. I just noticed recently.
You might have seen videos like this before.
Not that one. I don't pay for the special YouTube, that's why I need to watch this sometimes dumb.
But here's the big secret. Anyone can make one of these videos in a few...
Elon Musk might be grabbing the headlines for his exploits in space, which, needless to say, is not undeserved. When you dare to put people permanently on another planet and build the most powerful rocket that is also reusable, the revolutions are bound to attract attention. However, there's another revolution of Musk going on this planet that you might not have heard about yet, which will change everything as we know it. For years, Tesla has been working on what is the most powerful computer in the world, the powerful near-quantum supercomputer. What is this near-powerful computer and how does it affect it?
Just let me stop here for a second. One of the most hot topics these days is the quantum computing. I had an idea, we are not there yet. And I cannot tell for sure we are there or not, but this video shows we are maybe there. Who knows?
You as a person. Join us as we dive into Elon Musk finally revealing its new powerful near-quantum supercomputer. Is Tesla a car maker or an IT company? Tesla makes sweet and fast cars powered by batteries. It is even a leader in EV batteries, so it is not surprising that most of the world identifies Tesla as a manufacturer of battery-powered vehicles. However, the fact is, the Musk-controlled company is much more than that. The line between a car-making company and a computer-based company blurs when Tesla is involved. For example, it is not without reason that Tesla has a market capitalization in the league of IT companies. The market cap of over $1 trillion, Tesla rolls with the big boys like Microsoft, Apple, Google, Facebook, and Amazon, far removed from companies from its own primary industry. Toyota, the second most capitalized automaker, has about 1/4 of Tesla's worth, while Volkswagen, the third, comes in even lower at about 1/8. Not surprisingly, Tesla has championed over-the-air updates to make its cars better by adding features or clearing bugs, just like Microsoft updates your personal computer or Apple releases an update for your iPhone. Speaking of software, Tesla is the leader in auto software. Tesla has in the past unlocked more battery capacity over the air, although not everybody liked the idea. Over the years, Tesla has refined its user interface so much that drivers use it without even thinking about it. Tesla even has games for you to play on your center console and Netflix for the times you want to chill inside your car. While that might be controversial sometimes, it shows how seriously Tesla takes software. And that's not to talk of hidden Easter eggs that make the ownership experience much more exciting. This is all why Musk said the Model S was not a car, but a sophisticated computer on wheels. Here is how Musk describes Tesla. Tesla is a software company as much as it is a hardware company. A huge part of what Tesla is a Silicon Valley software company. We view this the same as updating your phone or your laptop. That was back in 2015. Since then, Tesla has improved in both hardware and software, but the company is still as focused on the software. Most recently, Tesla's AI head, Andrej Karpathy, describes Tesla's car like this. We are effectively building a synthetic animal from the ground up. The car can be thought of as an animal. It moves around autonomously, senses the environment, and acts autonomously.
So, if you like, you can finish it at home. What was a surprise for me, this guy, this Karpathy, has a Hungarian name definitely, and he was born not far from here, from Budapest. And then he had a great fortune to study in the best places on earth. You can read his thesis, his PhD. I read it. Fascinating. Not easy reading. I put you the reference for you in the literature if you like, and it is fascinating. What is his aim? He's leading the Tesla autonomous car project. They are building artificial animals. Those animals who are on wheels instead of walking on four legs, cars. And what was a great surprise for me, and the explanation why they built this huge so-called near quantum computation center to process this huge amount of data what the Tesla car can send in. What they said, they do differently than the other car makers. Instead of using this radar on what scans the environment around the car, they're using 8 cameras. What cameras looks around in a car and send it back to this computation center, and some artificial neural network will learn what are those objects on a photo, on a camera picture. Where are the curbs? Where are the traffic lights? Where are the persons? Where are dogs? Where are trash cans? Something like that. And based on this training, the device, the car, can decide what the camera sees. Fascinating. And it is not a far future. It is very close. Within years, we can see the result of that. They invested huge amount of money in it, and with a good reason. If you will read his thesis, you will be convinced it is close. So this is what I wanted to show, and go back to the presentation. And here it is. Just go back for a little when it is started. You can think it was started maybe 10 years ago. No. It was started just many, many decades ago. The parallel, the digital computers and the analog computers was born on almost the same time. As you know, the digital computers had a great boost during the Second World War, because they needed a lot of calculation for calculate these weapons or the cannon, how to set up the cannons. And based on this lot of calculations they learned, it can be used for many other purposes. Great. And now these days we are benefiting from that. But at the same time there was another approach. For example, this guy, Frank Rosenblatt, introduced his method. What he did, he put a screen and projected different letters on it, A, B, C, D letters. And the screen was 20 by 20 resolution, very coarse resolution, very bad resolution. But they connected each of these elements of this 20 by 20 screen to a photosensor, and instead of programming how to recognize different letters, they used the training sample, data, projected different letters on the screen, A, B, C, D, so on. And if the A was projected there, they said it is A. And if B was there, they said it is B. And when they told for the system, for this technology, that it is B, somehow they modified what was inside. And his metaphor was the real brain, the biological brain, using artificial neurons, like this here on this photo. They had some inputs. How many? 400, because 20 times 20 is 400. 400 inputs and 26 outputs, as many letters are in the English alphabet. Surprising enough, going through of this training sample several times, the system was able to tell it is a B or C or something like that. Instead of programming that, instead of writing a specific code how to recognize this B or C or something like that. It was a great surprise, great success and great surprise. And of course, one of the main tasks in the computer field is the pattern recognition, to recognize patterns. What kind of patterns? Any kind of patterns. Face, fingerprint, voice print, I can name it, or you can name it. And it's a basic task to recognize something. And it was a very simple example to show that it can do. This system can somehow recognize. They can somehow identify without programming. So there was a great excitement, and then the military leaders had to decide it is worth to put money in it or not. And they asked the most leading guys in a planet to evaluate the system, and I will tell you the results soon. So that time, when it was started, the scientific people had some understanding how the neurons works in the biological brain. And it is the most simplified version of it, when it was a very first model, so-called McCulloch model, showing that each neuron in a real brain, in a real nerve system, has a cell. And the cell has some inputs and has only one output. This is the basic element of the nervous system. A cell who has inputs, and one output. And it was the model. For example, each of these elements has some inputs, I1, I2, IN, altogether n inputs. And then somehow this device or this neuron can summarize these inputs, add together. Not just simply adding I1, I2, and so on. Each input multiplied with some kind of influencing factor. They called it weight. That's why we name it W in English. So the input for the I1 is I1 multiplied by WI1. This is the total influence for this cell. And then if we add it together, this represents this S here, the sum. multiply all of these inputs, multiply by weight values, and adding together, this is the so-called excitement for the neurons. This is the very basic understanding how the biological neuron works. Clear? When we have this sum, there is a t value inside, meaning that transfer function, meaning that how the neuron will react for the sum, for this S, for the excitement. It can be linear, it can be some kind of strange function in it. The original idea was that if the sum of these values are smaller than 0 or equal to 0, then the output is 0. But if the output or the sum is more than 0 or equal to 1 between the range, the output is 1. Clear? So if the excitement is less than 0, it is 0 the output. If it is more than 0, it is the output. Some kind of step function. Based on this very simple neuron, they build a perceptron and ask this very famous guys at MIT to evaluate it. And this guy was Marvin Minsky and Samuel Papert, the two authors, who published a book about it called Perceptrons. And in this book, they told it is not true, not good. It can solve only so-called linearly separable problems, or using other words, toy problems. For example, if there is an n value here, this here, this here, logical value, input 1, input 2, and this is the output. If input 1 is 0, input 1 is 0, the output is 0. Input 1 is 0, other input 1 is 1, it is 0. It is only 1 if all of them is together 1. It is called the AND function. 1 and the other one is true in the same time it is 1. This is the logical AND. And if you represent this whole in this graph, this is the input 1, this is the input 2, this is the truth value, this is when it is true, and this is when it's false. So we can put a line between that. Same thing applies for the OR value here. This is the OR logical function table. And this is true, 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 and this is the false. Only when both of them is false. We can put a line between that. This kind of very basic perceptron, very basic neural network, can differentiate or classify or recognize only this kind of toy problems. But if the situation looks like this, for example, the very simple version is the exclusive OR. When one of them can be 0, one of them can be 1, and that is true only in these two cases. One is 0, one is 1, or one is 1 and one is 0. This is the so-called exclusive OR logical function. And in this case, we have 2 1s and 2 0s. And this very basic perceptron cannot recognize it. Meaning that we cannot recognize faces, we cannot recognize voice prints, anything with kind of very simple perception. Because of that, the whole research stopped for decades, because everybody read this article, and everybody believed to Minsky and Papert, and said, okay, we cannot get any support for this kind of research. So this is the history of this whole situation. And many years later, as you think, many years later, this topic came back again. And I made a new analysis and learning that this two guy was wrong, because they didn't consider something new possibilities. And I will show you this today is what is this possibility. So this Papert, one of the authors, published the article about it. How did he feel to stopping this research for decades? He told the story of the Snow White. When the Snow White was sent, as you know the story, the Snow White's tale, the Snow White had to go to the forest because her mother, the stepmother, was not fond of her. and she wanted to made him killed by the hunter. And the hunter did his job, but was there to kill this lady, this young lady. Rather, he showed the heart of the pig, showing that it is her heart, but it was not her heart. So later on, the Snow White appeared again, and as you know the story. And he says, this Pepper says he had the same feeling, because he killed this topic for decades, showing the fake proof, the heart of the pig, instead of something useful. Now this is back, and as I will show you soon, the comeback was very interesting, very simple. Two guys published the article in Nature. It was 4 pages long article. And if you are interested, you can read it. I gave you a reference. You can find it easily on the internet. And then it was a game changer. And now we are back again. And let me show you what are those main elements of this new paradigm. First, these are constructed simple processing elements. Instead of making a many core, very complicated instruction set processor, what we have in our devices these days, they are a very simple processor, very simple one, just like what I show you, this McCulloch Basic Neuron. Second, they are not programmed, rather trained. We can teach it using human words, presenting data for that, and based on the data, it will somehow recognize something, it will classify or understand something. The third one, the knowledge in the network is distributed. If you take out one part, nothing happens, just like in a real brain. If some part somehow has some damage on it, the whole creature won't die right away. Maybe they will recover. Same thing happens for artificial networks. And then, because of this capability of tolerating errors, the system is fault tolerant. Some part of it turned wrong, no problem. It is still working somehow. Fascinating. And then we have 3 major elements. This is what I like to summarize you today and show you the basics. The first one is the processor. Very simple one. Make some summation, some transfer function, and that's it. The second, what is the key, what is the most important element in it? The topology, how to connect these very simple processors. Not easy to do that, and tell you the situation what I see, we are not even close to mimic the real brain. Because as I mentioned, one of the first slides, we have this complicated multiprocessor system in the human brain, for example, and we don't understand the connection between those, or especially don't understand what is a real purpose, how this specific area can achieve that specific task, to solve the specific task. Many people are on it, doing very extensive research on it, and some specific neural networks are already in use, but it is not a general purpose, it is a specific purpose these days. And finally, we need to learn how to train it, how to tune it, how to change it, how to modify it. This kind of synonym works for it. And if we learn how to do that, we can start to collect data, build a neural network, start the training, and based on the training, we could be very successful. And we can make something much better what all of other people in that field did before. Isn't it fascinating? It was for me. Let me show you the basic neuron, the basic element of the artificial neural networks. It is just like this here. We have inputs, I1, I2, I so on, till IN. And each of these input can influence the basic neuron with some kind of influencing factor, using other words, some kind of weight, meaning that how much the influence of the specific input. It is a number. It can be minus, or minus, plus, till plus, in a range. It shows what is the influence of the specific neuron input for the neuron. And then, inside the neuron, we have a summation feature. It sums it up. For example, this S here, this here S, meaning that the input multiplied by the weight factor plus another input multiplied by weight factor plus so on. Clear? This is the S here. This is the S. In most cases, this is how it works. It is so simple. What makes a difference, usually, the transfer function, this T here. How the neuron will react for this excitement, for these inputs, for this summation. One thing what I like to mention here, before I go forward, if I have two neurons like this here, name it I and J, and if I connect these two neurons with a weight, there is a very standard notation for that, meaning that W, meaning that weight. And in this here, we can see the J and I, meaning that it is connected to the J neuron from the I neuron. The WJI, subtitle JI, meaning that it's a connection between the I and the J neurons, but the connection is coming from the I as going to the J. Please raise your hand if you understand this. Okay, thank you. Very important, because later on we need to understand these very important connections. There is a list how to build neural networks. Very simple and summary. First we need to collect data, because this whole approach is a data-driven approach. We need to collect as many data as we can. Because if we don't have data, we cannot write a code. We are not writing a code. We just want to present the data. We want to somehow modify the network to be able to achieve the specific task. And if we want to do it right, we need to collect a lot of data. I will show you some examples how to do that. The second step is we need to design a specific, problem-specific neural network paradigm. One of the most common these days so-called convolutional networks. If you're interested, you can look it up. For example, this Kurt Academy focused, what I understand, focused on this convolutional network. But the Karpati, who I mentioned, who is the head of this Tesla research, his field was also convolutional networks. Fascinating. One specific type of neural network. I will show you the basics for that today. And then, if you have a paradigm, if you have a specific kind of structure, how to connect those elements, then we need to decide many small elements. For example, what will be the transfer function, this T? How will it behave? Then, and we need to decide how many layers it will be there. 2 layers is not enough, as Minsky and Pepper showed. At least we have 3 layers or 4 layers. The human brain has 10 layers. 10 consecutive layers connected these elements. And how to connect them, what connect to what? So not easy. That's why, so far, till these days, the design of neural networks was kind of black art. Because it's not as a straightforward method to do that. We need to have some good idea how to do it. We need to test it. And if that doesn't work fine, we need to change the design. And this is a reason why traditionally, the traditional artificial intelligence researchers, the engineers and mathematicians, hated this topic. They said it is good for students. The students has time, they can play around it, and then if you are successful, great, but I cannot prove it, why it is so successful. So it was the past, it was the last couple of decades. And I will show you some examples of what kind of great achievement the students made. Now, these days it became a mainstream. Then we need to decide what is good for us, what is the so-called target performance, what is the level what we can accept as a good problem-solving result. And then we need to decide how to test it. Since the training is a very time-consuming procedure, at the end we cannot be sure it is finished or not. Kind of trial and error, trying and changing. And then at the end we need to test it. And if the test shows it is okay, we will be happy with it. Problem here, we cannot ask the network so far, till these days, why? We cannot ask this question, why? It will recognize your face, but we cannot ask why, because there are no rules in it. There are no specific answer for this. We can see the weight, the interconnecting weights, but it won't give you an answer. So If you have a test procedure, we need to start the training and testing, training, testing, training, testing, so on. And if we achieve that good level, what we will be happy with it, we can stop training. If not, it's a problem. We need to start from scratch, start over, and do it again. So, as you see, we are at the beginning of this stage, even though we have great achievements, but within our lifetime, we can see a huge, unbelievable achievement in this field when we'll understand the network structures, what we don't do these days. Very simple example. If we have training data, for example, X, Y values, meaning that we need to tell which area want to find, this left or the right area here. We can have corresponding X and Y, X1 and X2 values. We can say this is the A, this is the B, and we want to train the system to tell us it is a A or B when we present to data, X and Y, X1 and X2. We have two inputs and we have one output. And the output can tell us A or B. The two inputs are the X1 and X2. For this basic problem, there was a very fascinating, very interesting achievement many years ago. The guy who studied here in Budapest had the fortune to go to Holland to study in another university. And in that other university, they had a specific VLSI processor building lab in a basement. So if he wanted, he was able to go down and talk to those people and said, I like to design a processor. I like to design some VLSI processor. I said, okay, do your homework and then you can do it. During this time, he learned there is a contest, there is a specific announcement by CERN, you know, where the big collision center is in Switzerland, announced there is a very specific problem. They had this extremely complicated and expensive colliders when they collide two different particles. And based on this collision, they're going to check what's happening there to understand the basics of the matter, our universe. But the problem was here, when this collision happened, they produced huge amount of data, 10 to the 7th megabyte of data, but most of this data was just a noise. Only 1 megabyte was an event, but they had to do a further research on it. But the problem was, somehow they had to somehow differentiate it is a noise, trash, or it is a useful situation, but they need to analyze it. But the problem, it happened in real time, so they had a special kind of so-called classifier, what classified it is trash or useful data, to tell which one is which one. And in do it in real time, there was no way to use a regular computer, because to use an algorithm, it needed much more time to calculate it. And the problem, as you understand clearly, there was no way to store this data, because there was a huge amount of 10 to the 7th megabyte of data. There was no storage device to store it. They had to let it go. They had to discard it. But they had to record this one specific kind of sample, what was about 1 megabyte. So this Moshe Peter was his name. He said, we have training samples. We have trash or not events, and we have events. A lot of this kind of data. The different sensors, altogether 70 sensors, produced this input. And then the researchers, the physicians, or the physicists, learned which one is the event, which one is not, later on, doing some analysis later on. But when it happened, in real time, there was no way to tell, because there was no way to store it. So he was able to get a lot of data, training data. And since he learned the basics of neural networks, what we do today, he decided he's going to build a very specific, very simple neural network, meaning that he will have 70 inputs from the 70 sensors, one hidden layer neurons, the very basic one that I just showed you before, and one output, what we tell it is an event or it is a trash. And I presented this data for this network, and somehow, step by step, set the interconnecting weights. The neural network can learn to change the interconnecting weights. Nothing has changed. The weights, these W's are changing. And I had to go back time to time, show it is even, it is trash, even trash, even trash. Within each of these steps, they had to modify the weight in the network. And he did it. And after a long session of training, he was able to recognize efficiently the event and the trash. And since he was in the fortunate situation, he was able to build the hardware for that. This is the VLSI hardware, what he built. Going back for 1 second, it was a basic structure, this one here, this here. And then this is the hardware, the processor. So when he built it, he tested, and this is the result. The classification was done within 20 nanoseconds. So within 20 nanoseconds, this device, this processor was able to tell it is trash. It is trash, let go. But if it's even, record it, put it on a hard drive and analyze it later on. It was a great success. He got a great job and probably working ever since from the CERN. And I talked to him many years later, and he was still working on this kind of classification features or this kind of problems. Another example what I like to show just very briefly. It was also great achievement. These days, when we have these talking machines around us, it is something not surprising. For example, how to pronounce letters or how to read loudly. We have computers in our pockets what can read any text for us. But way back, many decades ago, it was not the case. 40 years ago. There was no such thing, no such computer was able to read the text well. That time they had a rule-based systems to have different kind of rules. If such and such situation is in a text, you need to pronounce something like that. But that time, two guys, this Sejnowski and Rosenberg, one of them was a professor, another was a student, had an idea, why don't we try this neural network method? Instead of giving rules for the system, rather give a training data. Get a lot of data, a lot of words, a lot of text, and manually code how to pronounce the letters in English text. In Hungarian, it would be an easy task for us because we have a phonetic language. So if I write, for example, A in a character, in a word, we pronounce it A. If I put it C, I pronounce it C. But in English, not, because it is really environment sensitive. For example, if this word is enough, the O within this word, it is not pronounced O. You say enough. There is no O in it. And so on. So to be able to tell how to pronounce a specific word, they figure out they will do it following way. They coded a huge amount of words in a system to produce a training data, but they checked 7 characters in the same time. 3 before the character and 3 after the character. And they pronounced the middle one out of these 7. And they had this sliding window and manually write down how to pronounce this letter what is in the middle, within these 7 characters. The other traditional people who worked in this field said, oh, it is hopeless, it won't work. But this guy was persistent enough and made a good training sample, and finally they made better results than everybody else before. They presented the English text for that, and it pronounced properly. Great achievement. And during this testing, they learned something fascinating, intermediate results. For example, the system going through 5,000 times, or 500,000 times of this training data, the curve shows this is the learning curve, showing that how fast the system worked or learned. We can see it, for example, the stresses within the word learn much faster. And then the other elements of the test or the speech learn much slower. So just like humans do. The second, the system was able to learn to pronounce C to S 100% eventually. This is the curve here, this here. Eventually was 100% okay to pronounce C as a S. But to pronounce C as a K, what happens sometimes in an English text, was always some error in it. Some 5% of error. Regardless how many times they tested, they was not able to study, not able to learn. Next interesting thing was when they finally trained the network, it was 90% efficient and right. And they added some noise for the weight, some random noise for each of these interconnecting elements. The performance of the system was not totally disabled or destroyed. It was just decreased, something like giving more and more weight or noise. The performance went down from 90% went down to the 40%. And when they retrained the network, or gave back to the training again, it recovered much faster. This is the already trained network, recovered much faster, because they already had some data in it, some knowledge, distributed knowledge. What the point is here, this network behaves just like a human's, some kind of anthropomorph behavior. This is what we can experience these days using neural networks, something what the brain does. Fascinating. Please have a 5 minutes break, and I'd like to continue after that.